Okay, in the last video, we considered how to do an integral when you have a constant raised to a variable power. And here we have a similar type of problem, only now we have our constant raised to a variable power, but this variable x is multiplied by another constant. We want to see how could we handle this integration. And of course, it's very similar to what we did before. And in fact, let's just kind of take it right from the very beginning. And we said, well, let's think about it like this. If we have y equal to some constant raised to a variable power, well, this variable is multiplied by a constant. How could we determine what dy dx is? And we ended up taking the natural log of both sides. The natural log of y would equal the natural log of a to the kx. And because of properties of logarithms, that would equal kx times the natural log of a. Then, once we derived this, we decided, well, we could easily take the derivative of that. That would be easy enough. And let's take the derivative of this side of the equation. So here we'd have d dx of the natural log of y. That would be equal to d dx of the constant k times the natural log of a, which is a constant, times x. This is a constant, that's a constant, so this is just going to be these constants times dx dx, or this side of the equation is just k times the natural log of a. Now going back to here then, this is going to involve logarithmic differentiation, and that's going to be 1 over what's inside the log sign, 1 over y, times its derivative. So we're going to have 1 over y dy dx. This just pops out when performing logarithmic differentiation. And it has to be equal to k times the natural log of a, or then dy dx multiply both sides of the equation by y, with y times k times the natural log of a, and there it is. But remember what y is. Y equals a to the kx. So what we have is, if y equals a to the kx, dy dx equals y, that's this, a to the kx times k times the natural log of a. So finding this derivative is actually pretty simple. And then notice here what we have now. We have dy dx equals a to the kx times this constant. Now, if I multiply both sides of the equation by dx, I'm going to have this constant raised to a variable times a power times dx. And that's exactly what we have inside of this integral sign. A constant raised to a variable power times another constant. So let's go ahead and do that. We're going to multiply both sides of the equation by dx and divide by this. So we're going to have a to the kx dx will equal 1 over k times the natural log of a times dy. For the integral of this, these are just constants, will equal this integral. So this will equal 1 over k times the natural log of a times y. But y is this. So we get an expression for this integral here. This integral is just 1 over k times the natural log of a times this expression, plus an arbitrary constant of integration. So we go back to what looked like a very strange integral of 7 to the 3/10 x dx. There's our original integral, and that equals 1 over k, that's our k here, 1 over 3/10 times the natural log of a, that's 7, times this, which is this. Oops, here we have the natural log of 7, times 7 to the 3/10 x power. A to the kx. This is our a to the kx plus an arbitrary constant. And there it is. So this looks like a very strange integral. As you can see, it just really falls apart. It's not difficult to solve at all. But again, it all harkens back to what's involved with logarithmic differentiation, so that when we have this kind of situation, we can determine what the derivative is. Then from that, we were able to derive this general formula for this type of integral, and then after that, it's just a matter of just plugging in the parts. So, okay, hope that was helpful. Come back and join us for some more videos, and we'll try and work some more problems.